keep it 10 minutes or so. So what I want to talk about here is a methodology that we have devised for pre-cooling a building, but largely a data-driven approach which plays a key role in trying to reduce the peak demand and therefore the energy costs of operating a commercial building. So this is joint work with my fellow collaborator Vikas in India, as well as Shiv, who is in the India labs, and Min Jiang, who was an intern working with me from CMU. Right, so a bit of Australia-centric perspective on energy consumption and trends. A recent survey performed in Australia showed that the energy bills were often in the top 3 list of operating expenses in major commercial and office-based buildings. Only behind municipal and council rates, land taxes, and of course some of the salary that they pay to their employees. What is more interesting also is the fact that the energy bills have risen by 82% between 2007 and 8 and up to 2013 and 14. So there's a lot of incentive for commercial organizations to reduce their operating energy costs in Australia. Another important factor here is that several of these commercial tariffs are fairly complex, and they have a variety of different components, starting from a demand charge. So you have a peak demand threshold. The moment you exceed a peak demand threshold, you incur a significant penalty, which is the peak demand charge penalty. And often peak demand charges account for anywhere between 30 and 70% of a typical energy bill. So there's a lot of incentive to reduce the peaks. In addition to that, there are these peak and off-peak energy charges, which is basically your cents per kilowatt hour that you pay depending on when you actually consume that energy. And in addition, you have a daily service fee of a few dollars per day, regardless of whether you use energy or not. So given all these kind of tariff structures, it is also not surprising that some of these other metrics from the US, many speakers have said before, that buildings consume a significant amount of energy, and business as usual by 2025, buildings could be the largest single consumer of global energy. So motivated by the recent trends, we analyzed energy consumption and demand data from a large building located in northern Australia. So it's in a very tropical region in the state of Queensland and not too far from the beautiful Great Barrier Reef in Cairns. And this plot essentially shows on the y-axis the instantaneous power draw from that building, which is the aggregate power consumption of that building, as a function of time for nearly a year and a half worth of data. So each blue is basically a blue dot which records the power consumption at 5-minute interval. And the red horizontal line that you see is the demand threshold. So this particular building has a 400 kilowatt peak demand threshold. So as long as you stay under 400 kilowatts, you're okay. But the moment you exceed that 400 kilowatts for even a fraction of time, in this case, the resolution is a 5-minute interval, you're penalized for that peak demand for the whole billing period, right? So there's a lot of incentive for this particular building to stay under the red line. So having analyzed this building, what we wanted to know is what are the reasons why this peak demand threshold is exceeded. And the plot here at the bottom basically shows the power consumption as a function of time for the air conditioning and the HVAC system on a particular day in summer. So this was for the 6th of January in 2014. Of course, Australia has southern hemisphere, so the summer and winters are different. So for a very hot day here in this region, what it basically shows is that nearly 60% of the demand that comes from this building can be attributed to the chillers in operation. And the remaining 40% are basically user-controlled essential loads, like your plug loads, your lighting, your elevators, and so on and so forth. And the reason why these chillers dominate is basically because this building has two chillers, a 300 kilowatt and an 800 kilowatt chiller. And they're kind of configured very naively. So they basically, the 300 kilowatt starts at about 6 o'clock in the morning, about 7 o'clock in the morning. Then the 800 kilowatt kicks in about 8 o'clock when people get into work. So they have occupancy sensors, they have temperature sensors, and all these things combined make the chillers, the load spikes really high when people get into work about 8 o'clock in the morning. And this is actually a reason why, or the dominant reason why the peak demand tends to increase, right? So what we observed just by analyzing this plot, and of course a variety of other plots that exhibit similar patterns, is that the cooling demand dominates in this particular building, right? And given that this is in a tropical region, you don't necessarily need heating. So the question we ask is, how can you actually reduce the peak demand to save on your energy costs? And the technique that we propose is basically pre-cooling. And the advantage here, of course, is that pre-cooling the building in advance of the expected cooling time, the intuition says that you can reduce the peak, and you can also time shift the peak into low energy tariff regime. So that's what we'd like to exploit in the rest of the paper. So pre-cooling a building, the concept of pre-cooling does exist before, but the two important factors that we are particularly interested here is how much in advance of the usual HVAC activation time should pre-cooling commence. And secondly, the second dimension that we want to exploit here is what is the set point temperature that you would want to choose while the building during the pre-cooling interval. So to do so, we use a kind of a data-driven methodology, because we had the building management system and the BMS data that is quite sophisticated. It's a smart building. They have lots of sensors installed in it. But at the same time, we don't want to rely on extensive sensor data. So we rely on very minimalistic requirements from a building management system, which is as follows. So the framework that we develop basically models the thermal energy balance inside a particular zone in a building. Essentially what it does is to predict how the temperature would evolve in a particular building inside the zone in a particular building, taking into account three key parameters. So basically the impact of the heat gain from the ambient conditions, the heat gain because of the occupants inside the building, as well as the cooling load imposed by the HVAC system. So with these three key parameters, we kind of indirectly estimate the occupancy. So what we call is we have opportunistic sources for estimating the occupancy. In this case, we have CO2 sensors, so which we use as occupancy information, but we can also use other forms of occupancy like workstation loads or Wi-Fi access point traces, or people badging in and out of the building as another indirect estimate of occupancy. So what we build is what we call a gray box thermal modeling for a particular zone level information. And it takes in a bunch of parameters from the building management system, as you can see on the left. The zone temperature data, the temperature of the airflow, the occupancy information, and so on and so forth. And also we feed in the control algorithm for the VAV boxes. And the reason we do that is to avoid the dependency on mass flow rate sensors, which can be particularly expensive compared to the CO2 or a temperature sensor. So if we have that data, that is well and good. But if we don't have that mass flow rate, then we can use the VAV control algorithm to kind of indirectly estimate the mass flow rate, which is what we do here. And then performing a simple regression analysis, the model kind of specifies, identifies a bunch of parameters. The details of this are actually in the paper, so I won't go into it. But what we do here is to get these parameters, basically doing a simple regression analysis to minimize the error between the zone temperature predicted by the model and the zone temperature which is actually recorded by the internal temperature sensors in the building. So we've validated this model by applying it to this particular section of the building, which is basically divided into 5 thermal zones, which is controlled by a single air handling unit. And because the occupancy sensor is for a per AHU level, what we do here is we take the average temperature across all these 5 zones as an average for the internal zone temperature inside the building. And they're kind of fairly similarly close, which is an office building, so it's not hugely different from one zone to the other. So the plot here shows the zone temperature on the y-axis as a function of time for a particular day. The blue curve shows the actual measurement, and the black curve shows the temperature predicted by our modeling approach, which shows that it's fairly accurate in trying to estimate the temperature. So once we get a handle of the temperature, then we can come up with a fairly number of different strategies, and I'll just show here an example of what a facility manager could do to using this approach. So let's say he wants to start pre-cooling the building at an ad hoc, say 30 minutes before the actual activation time, and at that point I'll set a temperature of 26 degrees Celsius. Here is the output of what we see. This is basically from simulation. The plot on the left shows the kind of scaled air conditioning power as a function of time. The plot on the right is the temperature evolution inside the zone as a function of time. The dotted lines are the baseline as the method used today. The blue curve is the result of the model. What we see here is that by reducing the peak and time shifting it half an hour before the actual activation time, you can reduce the peak by about 9.5%. This may not be really surprising, but I think it's nonetheless, it plays an important role in trying to reduce the peak for this particular building. And I want to quickly point out also that the y-axis here is actually a normalized air conditioning power. So we've just normalized it to the per unit thermal capacitance of the building. But if you were to multiply it, you will actually get the power in kilowatts. And the reason we normalize it is because we want to keep these results independent of the size of the zone. So it's easily transferable across different zones. So given that this ad hoc strategy, I mean, you can envision any number of ad hoc strategies, and it has various trade-offs between reducing power consumption and increasing energy costs and settling time as well. So a more systematic methodology combining an optimization approach provides a holistic solution. And this is something that we are currently working on, which helps reduce the expected energy cost, bounding the peak demand threshold using the internal temperature comfort range, and of course using the zone energy balance as before. And the optimization basically shows the following results. So the red curve is the business as usual in the plot here, whereas the black curve is the result of the optimization. And it essentially shows that you can actually reduce the demand, at least in theory, fairly significantly, right? So you can reduce the demand by nearly 50%. By time shifting the demand and using the temperature flexibility of the internal zones, you can exploit, you can reduce the temperature, you can reduce the energy consumption, and the two lead to a win-win in terms of reducing demand, consumption, and energy cost. So I'll just conclude with the last slide. Buildings are a major source of energy consumption, particularly so in Australia, where there's a major incentive to reduce energy cost. We've devised a simple framework driven from a data-driven methodology that we hope to have a win-win-win for reducing demand, energy consumption, and cost. The trials are currently underway in this particular building, and if you have any data that you'd like to share with these parameters, we'll be very happy to look at it to see its applicability. So thank you very much.